Hi, everybody, and welcome back to Statistics for the Behavioral Sciences. In case you might have forgotten, my name is Frank Losciavo, and I'm your instructor. Today, we want to begin a basic introduction to statistics. And although we're going to cover a lot of topics, for right now, I really want to make sure you understand how statistics fits into the scientific process. So let's start right there. Let's begin by talking about science in general. You probably have a pretty good idea of what science is, but you'd probably also have a difficult time defining it. One way to think about it is that science is just a method of asking questions and finding answers in a very controlled, thoughtful way. Let's assume for right now that I'm a psychologist who studies depression. Well, science really begins with researchers forming theories. So, for example, I understand that human beings are electrochemical machines. Our bodies communicate internally via neurons and neurotransmitters, which are just chemicals, hormones. And my theory is that there is a key neurotransmitter, namely serotonin, that is related to a person's mood. Well, that's a good place to start, but that's just a theory. And in order for something to be scientific, we need to test that theory. So the second thing that I want to do at this point is generate some type of testable hypothesis. So along with some friends of mine in the pharmaceutical industry, let's say we create a compound that is known as a serotonin reuptake inhibitor. And what it does is it puts more of this chemical, more of this neurotransmitter between neurons that are trying to communicate. And because I believe that serotonin has some effect on a person's mood, I think that people taking a serotonin reuptake inhibitor will actually have a better mood if they started out depressed. Are you starting to see how that's testable? We can actually design a study and test that to see if there's any evidence to support it. So that moves us down to this third step. Now we want to actually design a study. And in this case, a great way to test this would be via an experiment. In a simple experiment, I might compare two groups. So in this situation, I'm going to find some people who are depressed, who are interested in a new treatment. I'm going to assign half of them to receive this new drug, a serotonin reuptake inhibitor. And then I'm going to assign the other half of these depressed people to take a placebo. So all of the people across the two groups in this study are receiving some type of drug, but it's only half of the people in the study who are receiving a drug that has an active ingredient. After assigning people to one of the two groups, we're going to collect some data from them after a couple months. And of course, I can collect all kinds of data. I might ask the people directly how they're feeling. We can also utilize some professional psychologists who are conducting a clinical interview who will actually try to determine to what extent these people are depressed or not. So that's an important part of the process. We need to determine exactly what data we want to collect. You can see, based on what I just discussed, that the scientific process is really based on observing things, in this case, these people who are depressed, and then taking various measurements. Science is always based on those two things, observation and measurement. So at this point, we can ask ourselves, where does statistics fit in? Well, if you think about it, based on what we just said, science is really just a method of collecting data. And now it starts to become much more obvious where statistics fits in, because statistics provides us with tools for analyzing that data. And we're going to need some pretty good tools in our toolbox because data can become overwhelming very quickly. Let me give you an example. I'm obviously in a teaching profession, and I've always been interested in technology. So when people first started taking computerized tests, I started to realize that many of the testing strategies that students used to rely on, they're no longer able to use. So think about it. When you take a test, a written test, you might underline important words in a question. If you have to select an answer out of many options, you might look through those options and cross out the ones that you know are wrong. You might put a question mark in front of the entire question because you're not sure about your answer and you want to come back to it. These are basic writing strategies that people have used for a long time, but when you're taking a test on a computer, you're no longer able to use those strategies. I wanted to design a study to see what would happen if you took all those strategies away from somebody. Specifically, I wanted to know if it would influence their final score. So I recruited students from surrounding counties to come to campus to complete a retired version of the ACT test. They understood that when they came in, they would take a real, authentic, retired version of the ACT under authentic testing conditions, with one caveat. Some of the students would be allowed to write on their exam booklets, but others would not. So I designed a simple experiment. There were two groups. They all took the exact same exam in the exact same situation, except some people were allowed to write on their exam booklets and others were not. When I say that data can be overwhelming, just keep this in mind. I had hundreds of students taking this test, and the test takes several hours to complete. So for every single student, there were hundreds of questions that I had to look at. And for each question, I needed to determine, was this a student who was allowed to write on the test or not allowed to write on the test? If they were allowed to write on the test, I had to determine, did they use a writing strategy for that particular question? And if they used a writing strategy for that particular question, what writing strategy did they use? How could I possibly make sense of all of that data just within my mind alone? I couldn't. In other words, I needed some tools to help make sense of all of that data, and that's what statistics provides. Just in case you're interested to know, there were no differences between the two groups. So telling students that they're not allowed to write on the test booklet had no effect on their final score. However, I also asked them a variety of questions about how fair they thought the test was, and the students who were prohibited from writing on the test did not perceive the test to be as fair. So that was kind of interesting. That brings us to a good definition of statistics. Statistics provides us with standardized methods and rules for organizing, summarizing, and interpreting the data that we've collected. We need to organize the data just to make sense of it. We need to summarize all of that data so that we can communicate it effectively to others. And we have to interpret our data so that we can act on the results. What good is designing a research study and collecting data if we're not going to act on the results? So, statistics is all about making sense of data. Let's move on and talk about another topic that's related. Because when we collect data, we typically want to learn about some entire group of people, an entire population. But the truth is that populations are often too large for us to measure completely, so we usually need to measure samples from that population instead. Let's discuss that. So here's the point that I just made, that populations are usually too large for us to measure. They're not always too large, though. I mean, if I wanted to measure the population of Psych 2110 students at Ohio University, I could probably measure all of those students. It wouldn't be all that many. But if I was interested in learning something about the population of depressed people in our country, that would be something that would be impossible to measure. There are simply too many people, and it's too hard to define who all those people are. Well, here's the good news. Luckily, random samples are likely to result in what we call representative samples. Whenever you realize that an entire population has not been measured, but a sample was used instead, you always need to be asking yourself, is that sample representative of the population? We can only learn about a population from a sample if that sample appropriately represents the population. So let's delve into what that means, representativeness. For a moment, just think about an Austin Powers movie. There's Austin Powers and there's Mini-Me. Mini-Me is just like Austin Powers in all important ways, at least in terms of how he looks. But he's just a smaller version. That's how a sample should be. A sample should be just like a population in all important characteristics, except it just contains fewer people. So, if the depressed population has more females than males, then I would want to make sure that my sample of depressed people has more females than males. If most depression in society is composed of younger people and older people, I would want to make sure that my sample of depressed people contains younger people, teens, 20s, and older people, senior citizens. Do you see what I'm getting at? If I'm trying to learn about that entire population, but I can't measure all of them, one way that I can learn about them is by measuring a sample that is just like that population in all important ways. So how can I maximize the likelihood that my sample will mirror the population in important ways? The answer is that I can use a random procedure to select people for that sample. If I use a random procedure to select people from the population to be included in my sample, then all people will have an equal opportunity of being chosen. And when all people in a population have an equal probability of being chosen for the sample, then it turns out that the sample will have approximately the same characteristics as its parent population. But I'm sure you can already see where I'm going with this. It's not like a sample that's randomly chosen is going to be exactly like a population. There are going to be at least some differences. Those differences are natural. But when we use random sampling and we have a sample size that's relatively large, like for example 1,600 people, then our sample will mimic the population with great precision. Think for a second about presidential polling data. If we measured about 1,600 people, which is a pretty large sample size, and we asked them who they plan to vote for in an upcoming election, our sample is likely to give us an answer within about 2.5 percentage points of the correct answer. That's pretty darn good, considering that millions of people will vote in a presidential election. So I'm not saying that sampling is perfect, I'm simply saying that when we use a random procedure to select a sample, we can maximize the possibility that that sample represents the population. Because this point right here is really important. Sample data is essentially worthless if it doesn't represent the population. If we spend a lot of time measuring a sample that does not mirror the population, what have we learned about the population we're interested in studying? Not much. Now, practically speaking, we use some different statistical terms and some different notation when we're talking about data that derives from a population or a sample. Let's talk about that next. Information that comes from a population is known as a population parameter. And information that comes from a sample is known as a sample statistic. Let me give you a couple quick examples. The number of clinically depressed people in the entire world would be a population parameter. That's simply a characteristic of the population, the number of depressed people. So when we're writing up a research report regarding that data, we would have capital N represents the number of people, equals, and then some number. But I mentioned to you that population is way too large to measure. There's no way that we can ever capture all of that data. So it's likely that we would randomly select some depressed people for our sample. Let's say we measured 1,600. So the sample statistic in this case would be the number of people in our sample, small n equals 1,600. So capital N, the number of people in an entire population, lowercase n, the number of people in a sample. Let's say I'm trying to figure out the average age of a clinically depressed person in the population. If I had access to all of that data and I was able to take all of their ages and compute an average, that would be an example of a population parameter. Again, it's just a characteristic of the population, in this case, the average age. The way that we would show that in a research report is with a mu. That's a Greek letter mu right there, mu. We often use Greek letters to represent population parameters. So let's say the average age of a depressed person is 32. I just made that up, but let's say that's true. In a research report, I might list mu equals 32 years old. However, let's say I didn't measure the entire population, but I had a sample of 1,600 randomly selected people who are depressed. And of those 1,600 people, I computed the average age, and I found out that the average age was 32. In that case, I would put X bar equals 32. X bar is a sample statistic. Again, it's just a characteristic, but in this case, it's a characteristic of the sample, the average age. So I hope you can see where we're going with this. We typically have to measure samples because populations are too large. So what I'm going to do is be able to calculate a variety of sample statistics. I want to use those sample statistics to learn about the population parameters that they represent. In other words, by studying a random sample of 1,600 depressed people, I'm trying to learn about that population of depressed people. This goofy graphic might give you some idea of how samples and populations work together. In our example, the population of interest would be all of the depressed individuals in our world. Because I can't measure all of those people, I'm going to select a sample of those people from the population. and it works best when we use a sampling procedure that randomly selects those individuals. Once we select those individuals, we can collect data from them, and then the results that we glean from that sample can be applied to that population of interest. So instead of seeing populations and samples as being completely different, see them as working together. We collect data from a sample to learn about a population. I have sample statistics so that I can learn about population parameters. But now keep this in mind. Random sampling works best when we're trying to learn about some unmeasured population. Random sampling. Other sampling methods don't usually work as well. Let me give you two examples of other sampling procedures so that you can contrast these sampling procedures with random sampling. Another commonly used sampling method is known as convenience sampling. And that's when a researcher chooses, as his or her research subjects, people who are convenient. So again, let's say that I'm a researcher who's interested in studying depression. Who's convenient to me? My students. So I might determine of my students who's depressed, and then I can study those people. But do you see how those students are likely to be different from the average depressed person within the world? First of all, these are students, so they're likely to be more educated than the average person. They are students taking a psychology class, so they might be more interested in psychological issues. In other words, a convenience sample is likely to differ from a population in many important ways. Another sampling method that usually doesn't work quite as well as random sampling is finding what we call a self-selected sample. So I might put an ad out on the internet, I might put flyers up around a community asking for people to take part in a study of clinical depression. And now interested people would contact me to be involved in the study. Again, you can see how that sample is likely to be very different than the general population of depressed people. People who select themselves, for example, might be more motivated to get help. People who select themselves might be more open to discussing their own depression. People who select themselves might be different in all kinds of important ways. What's my point? A self-selected sample is unlikely to represent the population of interest. So if that self-selected sample doesn't represent the population, I can collect lots and lots and lots of data, but I'm still not going to learn accurately about that population of interest. Okay, I think that's enough for right now. Remember, we're just trying to learn where do statistics fit into the scientific process. The next time we get together, we'll talk about some different statistical procedures, and we'll also talk about different types of data. So in the meantime, let me know if you have any questions, and be safe.